Good morning to all. Today we are going to discuss about superconducting materials. First we will start with basics of superconductors, then Meissner effect, persistent current, critical temperature, critical magnetic field, isotope effect, type 1, type 2 superconductors, Cooper pair, BCS theory of superconductor, high temperature superconductors, Josephson effect, squids, cryotron and magnetic levitation. First introduction, it was thought that electrical resistance of a conductor becomes zero only at absolute temperature. But early 19th century, Owens studied the properties of mercury at low temperature using liquid helium. And it is found that the resistivity of mercury drops to zero at 4.2 Kelvin temperature. Next, Matheson rule. It states that the electrical resistivity of a material is sum of the residual resistivity due to the scattering of electrons by the impurities and ideal resistivity due to the scattering of electrons by the phonons. See, this is the formula for total resistivity. The definition of superconductors, the ability of certain metals and alloys exhibits almost zero electrical resistivity when they are cooled to low temperature is known as superconducting materials. The maximum conductivity with zero resistance of 0 Kelvin. This is about superconductor. Next, Meissner effect. The same kind of behavior we have studied in Unit 3, magnetic materials. Here also, we are going to see the extended version of magnetic property of diamagnetic material is Meissner effect. And the superconducting material is subjected to a uniform magnetic field under the conditions that the temperature is lesser than the critical temperature and the applied magnetic field is lesser than the critical magnetic field. The magnetic flux lines are excluded from the material. Thus, the material exhibits perfect diamagnetism. This phenomena is called Meissner effect. See, the figure 1 is normal state. The figure B, superconducting state. When the temperature and applied magnetic field is lesser than the critical point, then they can behave like a superconductor. They are completely expelled all the lines of forces from the material. Persistence of current. Persistence current is one of the most important property of the superconductor. When a current of large magnitude is passing through a magnetic coil, they can behave like a magnetic material. Once you switch off the current, still the coil behave like a magnet because of zero resistivity of the particular coil material. Okay. Coil with persistent current act as a magnet. It does not require additional power supply to maintain its magnetic field. Persistent current experiments have shown no measurable decay over years. Example, when you are passing a current through the coil, they can retain their magnetic field even after 1 year. Okay, so the upper bound electrical resistivity less than 10 power minus 25 ohm meter compared to the copper resistivity 10 power minus 10 ohm meter. See the difference between classical current and persistent current. They satisfy the Ohm's law. The superconductors cannot satisfy the Ohm's law since there is no loss of current. Decay when source removed almost instantly, they become zero. They may lose their magnetic field. No observable decay, generates heat energy. Yes, the classical current generates heat energy. We all know that Joule heating effect. A persistent superconductor or supercurrent, they cannot generate any kind of heat energy. Coherence, incoherent electron motion, coherent quantum states, they can form like a Hooper pairs. Next topic is critical temperature. Critical temperature. See the graph along the x-axis applied temperature and y-axis resistivity. The temperature at which a normal conductor loses its resistivity becomes superconductor is known as critical temperature or transition temperature. Every superconductor has its own critical temperature at which it passes over into superconducting state. Depending on the transition temperature, superconductors are classified into two types. One is low temperature superconductor, another one is high temperature superconductor. See the graph. When you are reducing a temperature from higher to lower, see the dotted lines. If the conductor, if a solid or if any kind of metals, they can behave like a normal conductor since they will satisfy the Ohm's law, so that we will get a linear variations. Which means when you are reducing a temperature, the resistivity will be reduced. Whereas in the case of superconductors, the sudden falling of resistivity to zero along the x-axis. Okay, so this is called superconducting behavior. This temperature is called critical temperature or transition temperature. So based on the temperature, they will be classified into two types: low temperature superconductor and high temperature superconductor. Low temperature superconductor, the transition temperature or critical temperature is below 30 Kelvin. High temperature superconductors are above 30 Kelvin. There are some examples for low temperature and high temperature superconductors. Next is critical magnetic field. Similar like critical temperature, a very strong magnetic field applied to a superconducting material. It disappears superconducting nature. This is called critical magnetic field. Again, see the graph along the x-axis. There is a variations of temperature along the y-axis, change in magnetic field. At a particular critical magnetic field along the y-axis, critical temperature along the x-axis, within the boundary, they can behave like a superconductor. Beyond that limit, they will behave like a normal conductor. Next one is isotope effect. We all know that the behavior of semiconductors, we observed when we are adding some impurities, the resistance will be changed. Similarly, in superconducting materials, when you are adding some superconducting materials, superconductor, Meissner effect, persistent current, critical temperature, critical magnetic field, isotope effect, type 1, type 2 superconductors, Cooper pairs, BCS theory of superconductivity, high temperature superconductors, Josephson effect, speed, graviton, magnetic levitation. First, we are going to discuss about the introduction of superconductors. Earlier 19th century, Owens, K. Owens studied the property of mercury at low temperature using liquid helium, and it is found that the resistivity of mercury drops to zero at 4.2 Kelvin temperature and changes into a superconducting materials. We all know that mercury is a metal. When you are reducing a temperature, then the resistivity drops to zero.
Next topic is Matheson rule. It is purely based on the behaviors of resistivity of a material. It states that electrical resistivity of material is sum of the residual resistivity due to the scattering of electrons by the impurities and ideal resistivity due to the scattering of electrons by the phonons. Total rho is equal to rho 0 plus rho t. Definition of superconductor: ability of certain metals or alloys exhibit almost zero electrical resistivity when they are cooled to room temperature. Low temperature is known as superconducting behavior. That is the maximum conductivity with zero resistance at 0 Kelvin.